Hello everyone, I am Dr. Nitin Kumar Saxena. In my previous video, I have discussed with you the concept of electric current and Ohm's law. Now we will go further and we'll see what is the movement of electrons inside the conductor. As we know that if we are considering any conductor, okay, and in this conductor initially there is no electric field is applied. So what will happen when there is no electric field? All the electrons will move in random directions, and since they are moving in random directions, so we can say the velocity of the electron is called random velocity, and the overall movement of the electrons inside the conductor will be zero. Okay, why? Because all the electrons are moving in random direction. How random direction? Because they will, suppose the electron is here, so it will, suppose moving like this, it will strike with another electron. After the collision, it will come like this, after this coming like this, and so on. So what we can say? We can say if there are n number of electrons inside this conductor and this is in random movement. Why they are in random movement? Because no electric field is applied. So since no electric field, movement for electron, net movement for electron, zero. This time the velocity of electron is called random velocity, right? This time the velocity of the electron is called random velocity. If I am saying in general electron has velocity vi, like there are n number of electrons, so every electron has velocity like this. Suppose v1 is the velocity of first electron, v1 is the velocity of second, this is for third, this is general vi, till it will go till vn, because total number of electrons are n. So the sum should be always 0 because the movement overall is 0, and random velocity, the resultant random velocity inside this conductor is 0. Mathematically, I can write it like, with the help of summation sign, I equals to 1 to n vi, right? So this LHS can be written as this. So this is equals to 0. So inside the conductor, when there is no external electric field is applied, resultant movement is 0, right? So what we will say? We will say for any electron, if we talk, the average velocity is 0. Now suppose I am saying, okay, I am providing an electric field. I am providing an electric field like this. So if I am providing an electric field to this conductor, right, so what will happen? You see, for any electron, the force is given by, suppose the direction of electric field is this, so a force will act on this electron, and this force will be given by, you know the formula, F is given by QE. What is Q here? Minus E, right? And what is electric field? E. If I am saying the mass of this electron is m, so what acceleration this electron has? F upon m. This is simply F equals to ma. So minus E upon m. So this is the acceleration on each electron when an electric field is applied on the conductor, right? So now what will happen? The electron will move with this acceleration. Initially we have assumed that yes, since there was no electric field at that time, all the electrons having the random velocity, and we can assume the resultant random velocity, like suppose I am saying, okay, consider this electron is at this position, and now from this position it is coming to this position. When it is coming at this position, how it is coming? When it come like this, it strikes here with some other electron or nucleus, then it changes direction. So when it strikes here, at that time we can assume the speed, the velocity is 0. Right? So if the velocity is 0, then it will gain again velocity when it will come from this point to this point. And this speed, this velocity is due to the external electric field, and this is called drift velocity. What is this called? This is called drift velocity. Okay, so this means when we provide external electric field, the movement of the electrons in presence of electric field is called drift movement, and the velocity of the electron is called drift velocity. While there is no electric field, the movement of the electron is called random movement, and the velocity is called random velocity. Now, to find this drift velocity, what can I do? I can simply write that a formula V is U plus AT. This is linear equation. Okay, linear motion equation. So you see, if I am saying final average velocity is given by BD. So BD is what? Drift velocity. Is given by, initially the velocity was 0, and I am saying it is gaining the average velocity BD. Okay, so average velocity for any electron in this inside this conductor when we are applying this electric field is given by Vd equals to, now you put initially what we have assumed that they were in random motion, so after the collision they are at rest. Okay, so they will start to gain the velocity again. So this will be 0 plus, what is the value of A? We have seen here the value of A was, I am writing it here again, which we have calculated before, minus EE upon M. Okay, so substitute the value of A here. So minus EE divided by M into T. Is it fine? So this means you see, what is the time now? The question comes, what is the value of this time? You know that time is when electron travel from this speed to this speed, this place to this place. This is time. But you know there are number of collisions are taking place. So if number of collisions are taking place, so what we will put here? We will put some time, which will be the average time of all the collisions. In that way we can get what would be the average velocity. I am again repeating, since electrons are colliding with each other when we are providing this electric field, and this movement is called drift movement and this velocity is called drift velocity, and we are trying to find the value of this drift velocity. So what we are doing? We are saying that okay, there are number of collisions are taking place. The general speed, the general velocity of the electron, which is we are calling drift velocity, is the velocity of the electron, average velocity at any time. So to get it, what we are assuming that we are taking any one movement of electron just after the collision to the next collision, and at that time this as time will be the average time for all the collisions, right? And you know that this may be that this time is short, this is more, this may be much more. So this collision time is also variable, this is also not constant. So what we are assuming here, we are assuming the average time for each collision. Okay, and this average time for each collision we define as tau, and tau is the average collision time. Okay, so if this is the average collision time, so in place of T average, what can I write here? I can write VD equals to minus EE divided by M tau. So what is tau? Tau is the average collision time for the electrons inside the conductor when we are applying any external electric field. So I hope this concept is clear to you. How can we give the value of drift velocity? Right? So the drift velocity inside the conductor can be given by this formula. Right? Now move ahead and suppose this is a conductor in which electric field is working like this. Okay, the electric field is applied like this. So what will happen? Electrons will move in this direction. Right? If I am saying like the area cross sectional area of this conductor is A, right? Now since electric field is applied, so we can assume each electron, since external electric field is applied, so we can consider that each electron has drift velocity. Okay, so since external electric field is applied, so this simply means that each electron has drift velocity. And now I want to see that, okay, if I am taking any cross section like this, okay, this cross section is also A, right, because we are taking any cross section here, so the area of this cross section will also be A. Now in delta T time, how many charge, or we can say electron, will pass through this what I want to see, I want to see that if this is a kind of conductor which is cylindrical in shape, so for this cross section, how many electrons will pass through this cross section in delta T time, right? So if I am saying, okay, one more thing, I am assuming that n is a number which is defined as number of electrons per unit volume. Okay, so what I am assuming that this conductor has many electrons. So in many electrons, we are assuming that per unit volume, the number of electrons are n, right? So if number of electrons are n per unit volume, right? So you see that how many electrons will pass through this cross section in delta t time. So first you see, if the current, since electrons are moving like this, so current will flow. Okay, so what can I say? I can say for this section, if I am saying delta x as this is the length from this point to this point, suppose I am saying, okay, I am considering any cross section. Suppose I am considering for this, I am talking about this cross section, delta x. So my question is to find how many electrons will pass through this delta x in delta t time, right? So for this, you see the electrons in this delta x can be given by the charge particle will be I into delta t, because you know that I is delta q upon delta t. So this means this cross section has how many charge particles? Del q is I delta t, right? Now again you see, if I am saying the speed of the electron is Vd, the speed of the electron is Vd, drift velocity, right? So this means delta x, distance delta x, right, can be given by Vd into delta t, right? And if I am talking about the magnitude, we are not considering the direction of the drift velocity, so I can take like this. Okay, so this is the distance delta x can be calculated, that the electrons will travel delta x distance in delta t time, right? And what is delta x? Delta x is this. So in delta t time, electrons will move from this point to this point. How many electrons will move? That you can say that yes, you see, we have how many electrons in this area? In this area, we have electrons given by the number of electrons, per unit volume is n. So this means number of electrons in this volume delta x portion n times a, right, into del x. Is it okay? Because this volume is a, in area is a, and this length is del x. So what is the volume of this portion? A into del x, and n is the number of electron. So charge in this area, in portion, charge will be, you know that number of electron is this, and the charge on one electron is E. So we can say Na del x into E, right? If you solve this, what you will get? N E A del x can be written as Vd into del T. Okay, so what we find? We find that if electrons are moving from in this conductor from this surface to this surface, when we are providing this electric field, so for any segment, suppose I am saying segment is delta x, so how many charge will be there, will pass through this cross section? So how many charge or electrons will pass through this? So to get that, you see that the charge in this portion is given by this, and also by the definition of current, you know that when charge flows, we have current. So how many charge will flow? That can be defined by this. And hence this I into delta T I into delta T will be equal to NEA VD delta T. Now solve this. What you will get when you will solve this? When you will solve this, you will get the value. You will get the value of I is NEA VD. And what is VD? E upon M tau. Right? The value of VD, I am putting the value of VD E upon, I have told you previously that I am taking the magnitude only. So if you are taking the magnitude only, so take the magnitude of E also. Okay, why? Because E is also a vector quantity. So I am placing like this bar, this absolute sign here for E also. So you see now what you will get. You will get here the value of I is N E square upon M tau E. And if I divide this A by this, so I am putting this A here, I upon A. So what is I upon A? I upon A is given by current density. What is current density? J. J is also a vector. So I am putting this taking the magnitude only. Or in the vector form, I can write like this: J equals to N E square tau. This is fine. This is in the magnitude form, and here we are taking the vector form. So J and E both are the vectors, so I can put like this. This is the Ohm's law, which is given by sigma E, and hence if you compare with this equation to this, what is the value of sigma? And hence the resistivity can be given by this formula also. The resistivity in terms of N, E, tau and M. Right? So we know that resistance is given by rho L upon A, where we have seen these formulae that R is rho L upon A, where sigma is 1 upon rho. So how can we get the value of rho and sigma? By using the values of number of electrons per unit volume, charge on one electron, mass of one electron, and the average collision time of the electron. So in this way, we can find the value of resistivity and conductivity for any conductor. Okay, so I hope this concept is clear to you. How can we calculate, and you you can give the Ohm's law in this form also. J equals to N E squared tau upon M E, where this is sigma, and if you know the value of sigma, you can find the value of rho also. So I hope this concept, how can we get the value of rho and sigma for any conductor, is clear to you. The next point is mobility. So let's see what is the mobility. Mobility. Actually, mobility is a concept which is used to check that how easily electrons can be mobilized inside the conductor. Okay, so the term mobility is defined as this is denoted by mu first, and this is defined as the two vector magnitudes. Again I am saying this is magnitude because I am taking the mod. So the ratio of drift velocity with electric field is defined as mobility. In other words, you can say that drift velocity per unit electric field is defined as mobility. So what is this physical significance? The physical significance is that you know that when you are providing the unit electric field, so what is the drift velocity? Means whether the electrons are moving fast inside the conductor or moving slow inside the conductor, that can be defined by mobility. Naturally, if electrons can move with high drift velocity, so the conductor is having more mobilization, otherwise it has less mobilization. So in this way we can define the term mobility for any conductor. And if I want to write the unit of mu, so the unit will be, you see, meter per second for velocity divided by, for this, what is the definition, what is the unit of E? You know the formula, V is given by ED, so E is B upon D volt per meter, volt per meter. So meter will come up, so what will come? Meter square per volt second. So this is the unit of mobility. Okay, so now you put the value of Vd. You know the value of Vd. You have find E tau upon m. If I am talking about the magnitude only. Okay, so Vd upon E can be given as E tau m. Okay, so this means mobility can also be defined as E tau upon m, where m is the average collision time, m is the mass of electron, E is the charge on the electron, which is known 1.6 into 10 to the power minus 19 coulomb. And hence, if we know the collision time, then average collision time if we know, then we can get the mobility of electron of any conductor inside any conductor. So I hope mobility is clear to you. Now let us come to the point. We have seen that the Ohm's law is given as V equals to IR or J equals to sigma E. So these are the Ohm's law expressions. Now the question is, what are the limitations of Ohm's law where we cannot use the Ohm's law? Normally we say, okay, if we have this conductor having the resistance R, so normally V is IR. Okay, so see what are the limitations of the Ohm's law. So the concept is limitations of Ohm's law. So what are the limitations of Ohm's law? Again I am drawing this figure in which we have this R, this V. So for this R, for this conductor, the resistance is R. We are applying the voltage V and the current is I. So V is given by IR. This is simple Ohm's law. And if I want to draw this Ohm's law, so what I can draw here? Right? So if you see this, so what you will get a relation between V and I, which is given by this expression. And if you compare this with equation y equals to mx, so this is a straight line equation passing through the origin. Okay, passing through the origin with slope m. So what is slope here? M. Right. So this is the ideal condition for Ohm's law. But what happens? What happens if I am saying our materials are not following the Ohm's law? Then what would be the conditions in which they will not follow the Ohm's law? So the first condition is, I said that this should be the condition where we are increasing the value of current every time the value of voltage is increasing. But practically, if we are increasing the value of current, so what will happen? When we will increase the value of current, naturally, on increasing the value of current, what will happen? The charged particles will move more in the conductor. When they will move more, they will strike with other charged particles more. When they will strike with other charged particle, they will dissipate more heat. And in that case, it may be possible that after some time, in place of following this straight line, after this I, what is going on? Suppose I am saying I1. So after this I1, what is going on? This conductor is not following the path of this. Now it is following the path of this. And hence, we can say after this point, this is not obeying the Ohm's law. Okay, so there may be such kind of materials which do not follow the V equals to IR relation after a fixed value of current. When we will go on increasing the current, they will not follow this relation. And this is the limitation, that after a certain current rating, it may be possible that some kind of materials not follow this expression. Okay, the second is suppose ideally this should be the condition. Okay, this means always it will follow this straight line, but maybe some kind of conductor or material like this, what happens for the some materials, that when we are applying, the will happen, the current will flow in the other direction. Ideally it should remain like this, but now suppose it is not like this, it is like this only, or we can say this is like this only. Okay, this normally happens when we talk about semiconductor material like diode. Diode is one example in which the waveform goes like this, in positive and negative it goes like this. So it is also not following the Ohm's law. Okay, so this is the limitation, that it will not follow the Ohm's law. The third case may be okay, that a material is like this, that its waveform is something going like this. Okay, so you see for this voltage, three different currents are possible. Okay, so in such cases also these materials do not follow the Ohm's law, and hence we can conclude that it is not always possible that all the materials will follow the Ohm's law. That depends on the property of the material, that whether they will follow up or not, or maybe they can follow the Ohm's law at some stage. After that they will not follow the Ohm's law. So there may be two conditions, that if we are increasing the parameters, so up to one stage materials are following the Ohm's law, after that they are not following the Ohm law. And the second case, the structure of the material or the behavior of the material or the nature of the material are such that it never follow the Ohm's law. Okay, so there may be a kind of materials that may follow the Ohm's law or may not follow the Ohm's law. Okay, so if I give you a brief name of such materials, so we can say conductors, semiconductors, and last insulators. So materials normally can be defined as three categories. First category is conductors, second is semiconductors, and third is insulators. Okay, so the V equals to IR, they don't follow because they are insulator. They cannot allow the flow of current. In semiconductor they allow, but with some conditions. And what are the conditions? That is beyond this chapter scope, so we will not discuss it here. And conductors follow the Ohm's law but at some physical stage. So we can say that Ohm's law is applicable with some certain physical conditions. If the system is following the physical conditions, then Ohm's law will be valid, otherwise it will not be valid. So if, okay, normally normally we say that materials that follow Ohm's law as a kind of resistance. Inductance and capacitance also follow the Ohm's law, that we will also again not discuss here. We are not discussing here. And resistance follow the Ohm's law. So resistance may be designed in two ways. The first way is we can define like carbon resistance, and second is bound. The second is known as bound resistor. Okay, so resistor can be of two types. Bound resistor and carbon resistor. These normally are designed like this, that they have some material and the wire is wrapped like this on it, and such type of configuration is called bound resistor. This is made for low value of resistance, and it's not depend, or you can say it's less depend on the temperature. Okay, so if temperature is changing, so their value of R will not change much with temperature. That how the resistance value depend on temperature, that we will see later in this chapter. The second is the material which is made a very compact size carbon resistance. So normally these resistors are used for electronic based circuits. If you see any electronic device, you will see something like this, and this is called carbon resistance. So this is most popular popularly used in electronic circuits, and this is very compact in shape and their values may go to high level also, right? So this is normally used most popularly in electronic circuit. Okay, and there is very interesting technical concept that by watching any resistance you can find what is the value of this resistance. Okay, normally by watching the resistance we can get the value of resistance. How? Let's see. And this is called resistance color code. This is called resistance. Okay, this is here. So this is called resistance color codes. So if you have any carbon resistance, which I showed you here, like something, okay, so this resistance can be used in any electronic circuit, and by visualizing it only we can find what is the value of this resistance. So for this we have one color code. So let me make one table first for this color, number, multiply, right, and last tolerance in percent. Okay, so color is defined as okay, let me again write because we need more space here. So okay, so so BB Roy, GB, GBG, WGS no color. So if I put the full color name, so this is black, this is brown, this is red, this is orange, this is yellow, this is green. Okay, so this is green, this is blue, this is violet, this is gray, this is white. Okay, this is gray, white, this is gold, silver, and finally no color. Now start from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Similarly here multiply 1, 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4, 10 to the power 5, 10 to the power 6, 10 to the power 7, 8, 10 to the power 9. Right? 10 to the power minus 1, 10 to the power minus 2, and finally here for gold 5%, 10%, 20%. So how can we understand this? To understand this, you see, I gave for each color I gave number, multiply, and here for last three I am giving tolerance, right? So normally if I am saying, if I have a resistance like this and each resistance has lines, right? Each resistor, carbon resistor, has lines. Suppose I am saying this line is red, the second line is yellow, third line is orange, and fourth line is gold. Okay, so the first two lines give you a number. You see here, if you see here, for red the number is 2, for yellow the number is 4. So what is the number? 24. Right? The third line give you the multiplier. The third line is orange. So if you go like this, so what you can say, for multiplier you can go like this. This is for black, brown, red, orange, yellow, green, blue, violet, gray, white. Right. So you see the third line is orange. So for orange the multiplier is 10 to the power 3. So what we will do here, into 10 to the power 3. Right. And the fourth line is gold. Gold, for gold is, you see, gold we have this 5, for silver we have 10, for this no color is 20. So this means this gives you tolerance. So this means plus minus 5%. Okay. So this means if you have this resistance having the color red, yellow, orange, gold, so the value of the resistance is 24 into 10 to the power 3 ohm with plus minus 5% tolerance. This means its value may be go up to the 5% increase or below 5% decrease with 5%. So the value exactly may go plus minus 5% from this exact value. Okay, so I hope this point is clear to you. Let's have a more example to understand this. And I am saying, okay, again I am drawing new resistance. Wait, 1, 2, and of course, if there is no fourth line, so no fourth line, only 3 lines are there. So this means this resistance has 20% tolerance. So I am saying only 3 lines. So for 3 lines, if first line is suppose yellow, second line is suppose maybe anything violet, and third line is black. Okay, so yellow means 4, violet means 7. So first two line will give you the value 47 into 10 to the power. What is the multiplier? Black. Black means multiplier is 1. So this means 474. So I hope the concept of the color coding is clear to you, and yes, there is no fourth line, so plus minus 20%. Or value may go plus 20% minus 20%. Okay, so I hope the color coding is clear to you. On the basis of color coding, you can define the value of resistance for any carbon resistance. This whole method is for carbon resistance, which is popularly used in electronic circuits. When you will see any kind of electronic circuit, you may open your laptop, you may open your TV, radio, any kind of electronic device at your home, even your mobile also. When you will open, you will get some resistances inside it, and these resistances are carbon resistance. And for these carbon resistance, the resistance can be directly identified by only visualizing them. Okay, so I hope this concept is clear to you. Now let us move. I have given you the concept. I told you that Ohm's law is valid for the conductors in the specified range. What does it mean? That if we are increasing the value of the temperature, suppose, so what will happen? So for this, we see the temperature dependence of resistivity. temperature dependence on resistivity. Okay, so how the resistivity depends on the temperature. So you see, the formula is given by right. If we have any temperature T and initial value is 0, and we know that initially the resistivity is given by rho 0. Rho 0 is the resistivity at temperature T0. So rho 0 has resistivity at temperature T0, and rho T resistivity at temperature T. So this rho T, okay, resistivity at temperature T can be calculated by using this formula, where alpha is a constant and called coefficient of resistivity. Okay, and this is called coefficient of resistivity. And you see here that if I am talking about the two things which is more popular in the flow of current, like we always study the flow of current in either metal conductors or in semiconductors. Okay, so I'm separating the concept of insulator here because insulator does not have the concept of flow of current. No current flows in insulator. So I'm talking about the metal conductor and semiconductor. Okay, so what happens when we talk about metal conductors? The alpha is positive, and for semiconductors alpha is negative. This means if we are increasing the temperature of metal, its resistivity will increase. While if we are increasing the temperature of semiconductor, its resistivity will decrease. So normally we can define like this. If I am saying this is temperature, this is resistivity. So this is the graph for the conductor. Okay, and this will be the graph of semiconductor. Okay, so mathematically you can say temperature coefficient for resistivity is positive for metal, negative for semiconductor. So I hope this concept is also clear to you. So in this video I stop at this point. So the concept of resistivity and conductivity in metal and semiconductors is clear to you. How can we find the value of resistivity and conductivity? All the points are clear to you. Thank you very much.